welcome Dr. Aaron Parnes, leader for the Extreme Environment Robots Group at NASA's Jet Propulsion Laboratory. His work relates to climbing robots and how they might attach to their surrounding environment. And today he's going to tell us about the Gecko Grippers. Can you tell us how they are going to stick without being sticky in the harsh environment of space?
Yeah, my pleasure. So our work in my lab is all about robotic grippers. We use these grippers as the feet on climbing robots to go up cliff faces, across cave ceilings, or to move around in microgravity. We can also use these grippers as the hands on robotic arms to grab and manipulate things. For this experiment, we're inspired by one of nature's best grippers, which is the gecko foot. And geckos stick using something called van der Waals forces. They have lots of tiny hairs on their feet that allow them to take advantage of these forces. So if we could bring up the first picture. This is a graphic put together by Bob Full and his team at UC Berkeley. You can see on the toe of the gecko are flaps that are on the millimeter scale. You can see these with your eye. But on those flaps grow thousands of tiny hairs called setae. They're about 20 or 30 times smaller than the hair that grows on your head. And at the tips of all of those hairs is further branching, the nanostructure. These are called spatulae. They're much, much, much too small to see with your eye. That's what actually makes contact with the surface, and that's what takes advantage of these van der Waals forces. So if you bring up the next slide, you can see our robotic imitation of gecko skin. We're not quite as advanced as what the gecko has on its foot, and that's limited by current manufacturing capabilities. But you can see roughly the same shape. It has a directionality to it, and that's really important. That's how you turn the stickiness on and off. So if the gecko pulls down on its foot, it's very sticky. But if the gecko doesn't pull down, or if it pushes up or to the side, it's not sticky at all. So this is a good thing. If you're climbing up the wall very quickly and you're using something like duct tape, it might be just fine to get stuck on the wall, but you're going to have to pull with a lot of force to get it to unstick. And this is a big deal in space where there's no gravity, there's nothing to react to those forces. So having the ability to turn your adhesion on and off on command is really powerful. The other thing is it's a very reusable adhesive. So you can imagine if a gecko took 3 or 4 steps and the foot stopped working, that would be a bad evolutionary design. We've tested our robotic gecko skins in the lab 30,000 cycles on and off with no decrease in performance. We've also tested them hanging on the wall for a year and then reused them. And we've tested them in a thermal vacuum chamber at minus 60 degrees centigrade and in full vacuum. Because they rely on van der Waals forces, they're not susceptible to temperature, pressure, radiation, some of the things that make using conventional adhesives like duct tape and super glue not feasible in the space environment. So what we're going to do for this experiment is have the astronauts test 5 handheld grippers. This is the largest of these grippers, and they is a medium size and a small size. And to operate it, you squeeze together, touch down to the surface, and now it's stuck. We've got springs that are loading that material in the proper shear direction. But to turn the stickiness off, you simply squeeze together again. And so you can do this over and over and over again. We're only going to make the astronauts do it about 30 or 40 times. They're going to be measuring what the sticking power is by pulling on different parts of the grippers. And then we're actually going to leave one gripper in place for a full year, just to test the effects of long duration microgravity. And this experiment is really a precursor to some future capabilities that we'd like to see move up to the International Space Station and other activities in low Earth orbit. For instance, there are many sensors that we'd like to use that require a preload into the surface. Things like accelerometers, eddy current sensors, magnetic flux leakage sensors. But in space, anything you're pushing into the surface is pushing you away from the surface. So using a gecko gripper to react that load could allow us to use those kinds of sensors, reposition them in different places. A little bit bigger in scope, you can imagine using these as the hands on the robotic arms to assemble things in space, to repair satellites, to grab space garbage and deorbit it. Or my favorite application, because my background is robotics, is to put these on the feet of a crawling robot. have the robot go around on the outside of the space station, inspect orbital debris impacts, inspect micrometeorite damage, take pictures, take video, do all the sorts of things you can imagine a robot would be able to do. We're interested in these applications, these space-based applications, but there are a few commercial companies that are looking at making gecko adhesives viable here on Earth, either in a factory floor setting where you might be doing pick-and-place operations with solar panels or cereal boxes, or even in your home. You can imagine this material would let you hang your flat-screen TV on the wall without having to drill into the studs. And when you are ready to move or you just want to switch TVs, you can simply turn the stickiness off and put it on a different wall. So that's the summary. I'm looking forward to your questions. This is our first experiment going up to space station, so we are very, very excited.
All right, thank you. Please raise your hand in the room. Use hashtag AskNASA if you're following online, and *1 if you are on the phone. Again, please state your name, and please try to stick to one question, and if we have more time, we'll come back for more questions.
Yes, sir. Mark Gotch, Historical Space Imagery. Could you tell me, sir, the Gecko Grip that you currently have that you say the astronauts are going to test in space, right now here in Earth's atmosphere, how much weight will that particular grip support for how long, and how are you expecting that to differ in the environment of space?
Yeah, good question. So a gripper this size can support about 15 pounds on a smooth surface. As the surface roughness goes up, the holding power drops down, and that's because we don't have all of those complex hierarchical layers that the Gecko has. We expect it to be the same in space, and 15 pounds of force in zero gravity is actually a lot because things don't weigh anything, right? You're weightless, so you can move around really big objects as long as you keep the inertial forces low. But we haven't tested it. That's why we're going up there to do the work and make sure that that's actually what we see.
Thank you. We'll go back here.
Hi, Ken Kramer, Northeast Astronomy Forum and Universe Today. Talking about robotics, another application I want to ask you about is what about sending these to planetary bodies like the Moon, Mars, to go up and down mountains, hillsides, craters, large rocks, things like that. Maybe you send one if these are light enough on the 2020 rover.
Yeah. Planetary bodies typically are much rougher surfaces. And we actually have different gripping technology that we use for those rougher surfaces. So there's another technology called microspines that are basically lots of sharp hooks. It's also a bit bio-inspired. And that's what we use for our rock climbing robots. And it's actually part of the baseline for the asteroid redirect mission, which is going to grab a SUV-sized boulder using that kind of a gripper. So if you go on YouTube and you search rock climbing robots, or you search crazy engineering Gecko Gripper, you'll find little YouTube episodes that JPL has put together on these different technologies, and you're free to post those on your sites and all of that.
Here in the middle.
My name is Shannon Stewart. My question is, what's the biological basis for the gecko's hierarchical spine structure, and could that inform the manufacturing technology you need to improve?
Yeah, it's a good question. So geckos have that hierarchy in order to conform to the surfaces it finds in its environment, which aren't smooth composite panels like you're going to find on the space station. And so the hierarchy is really necessary to get all of those tiny, tiny nanostructures in good contact with the surface. And it's absolutely informed our design. There's been a nice collaboration between the experimental biologists at UC Berkeley, that's the slide I showed, and some of the technologists that are trying to make robotic versions of these. We simply haven't caught up to nature yet, but we're hoping to.
And we'll take one question from Ask NASA.
Indeed, Twitter user Derek asks about applications for other missions by saying, is the Gecko Foot technology to be used on the ARM mission?
Yeah, so the answer is it's not a Gecko technology, but it's a similar kind of gripper. So it's also work being done in our lab, but it uses claws. So the geckos use lots of tiny little hairs, but if you think of how a bear climbs a tree, it's using claws. And so we have a technology that's inspired by that kind of claw-based gripping called microspines. That's what's currently baselined for ARM.
Thank you. Thank you very much. And next we have Michael Snyder, who is the